Thank you, Andrea, and good morning, ladies and gentlemen. And it's first of all, a pleasure to be back in Italy, but it's also a big honor to be asked to be a plenary speaker following one of the world's greatest scientists today, John Delaney. It's as John was talking about, there's he has a habit of expressing all his visions, in particular when sitting over a beer in the bar. And I really would encourage the audience here to do that. We as engineers, I don't know, I'm sure you as well as I do, are quite intimidated by these scientists with these big visions. And just remember that von Karman said, scientists dream about doing great things, engineers do them. So I really think you should take up John on the invitation and have a beer with him, because that's really where he's coming up with these really crazy ideas. But on the other hand, because of people in this room and people like people in this room, the vision that John had, the one he threw up and put my name on, is very close to actually happening. And it's really an exciting time in that regard, and it's really a pleasure to be here and talk about that. Now, I'm even worse than John and more notorious in terms of running over time. So, and one of the things you always have to leave out in the end is the acknowledgements. So I'm going to start up with the acknowledgements. First of all, my staff and students back at MIT, without whom none of this work would have happened. But also the collaboration with CMRE, or as I prefer to know it, Sacklandson, because I spent several years, a total of 7 years at Sacklandson and NERC, and the people I've over the years have had the pleasure of working with, and I'm sure that this list is far from complete. It represents people, some of which are in this room, but I'm sure that I forgot somebody, because it really has been a tremendous time we've had together during all the cruises we've had, and I list all the cruises over to the right, where we have actually in the work we are doing at MIT, we've been involved in many more cruises with NERC and CMRE than we have with our funding agencies in the United States. But either, of course, have been important for where we are, and of course the funding by the various agencies is highly appreciated. So what I'm going to talk about is some of the history and particularly my experiences going through about 20 years now of working with underwater, with marine underwater systems, in particular coming from the area of acoustic sensing, which is really how I made my career. That's what I did when I was at Sacklandson in the first place, developing numerical models for sound propagation in the ocean, and then starting thinking about how can we, when this technology was emerging, how can we take advantage of that for acoustic sensing. So that's where I'm coming from, and that's what I'll try to do to give you some ideas about what is my experience in doing that. This is basically the outline of my talk, and I'm not going to spend time on talking about the outline for obvious reasons. I'm going to go on to the more of the content. And this is in my view, the most important slide. It's 10 years old now. John Potter thinks that I stole it from him, like a few of the other slides, but it's probably the other way around. At least that's my claim. It's the communication environment that we are facing in the underwater environment. If we think about each of us in this room sitting with a computer, we can network them instantaneously without any significant effort on anybody's part. They can talk to each other, they can talk to the cloud, they can talk to everybody can talk to everybody. Unfortunately, we don't have that luxury. And John was talking about this swarm of robots, and I'm going to talk more about that later on. And the beauty of the cabled infrastructure. Unfortunately, the cables doesn't reach, the fiber optic cable, John, doesn't reach out to those critters. They have to work, they have to be maybe connected at some point, but then they're going to be out on their own. And if we want to control them, we have to communicate with them. We are going to be faced with this communication environment. And it's really a layered communication environment, and that is really what is the most important constraint for the development of underwater or marine robotic systems. So if we think of having a platform like an AUV or a glider or a mooring, on board that node or one of John's critters, we have Ethernet. So we have virtually infinite bandwidth, and we can have information passing from the sensors through processing chains and over to the control of the platform, so we can have these various components on board the node communicating with each other and collaborating. And the control loop is very fast, so we can use sensor information, feed that back to the autonomy and to the control, and do that within microseconds. Is this not working anymore? I don't think the pointer is working anymore. Anyway, okay. So let me just speak to it. So that's what we are dealing with. If we are doing control loops on each node, we do that in a matter of microseconds. If we have to have two of these platforms talking to each other, we are facing a very different. Thank you. A very different communication environment. There we basically have to talk acoustically between the platforms, except when we are really at very close range. And the rates we're looking at there is, in our experience, and I know that there are people in the room who's going to jump at me afterwards and yell and scream at me and say this is not true, but the design number we are using, and that is based on 20 years of experience of doing this, is 100 bytes per minute, point to point. That's what we have to deal with when we have these platforms talking to each other. Now, if we want to if we want to do collaboration between these, we're talking about doing collaboration on timescales of minutes. Now, if we want to get even further up and getting the operator, getting John Delaney involved, then we have to go back up to the operator, and from the underwater world, getting back up to the system. If we are not near one of the cable nodes, we'll have to move and get into one of the cable nodes, and that takes some time. So we have some latency, and the order magnitude is 30 minutes. That's used, again, a design criteria we're using nowadays. Also, another possibility is going to the surface and talking via satellite, but so the data rates are higher up at that level, but the latency is significantly bigger. So if we want the operator in the loop, just as a general rule, we're talking about hours. We can look at phenomena controlling the assets underwater for investigating phenomena that are of the scale of hours. So now, if we really want to do things more efficiently, looking at small scales, small time scales, we really have to do it down here. And this is where this whole idea of nested autonomy is coming into the picture, which is the title of my talk. So, if another way of looking at this is this trait space for system performance. It has a three axes: the communication capacity in just a rough number, byte times the distance in kilometers per minute. And when we're talking land-based, air-based systems like the Predator drones flying over the Middle East, they can be controlled by a pilot sitting back in his living room in the United States. We're talking about 10 to the 12th byte kilometer per minute as the communication rate. So we really don't need much in terms of autonomy, because we have the operator. He can fly the plane. You don't need anything but an autopilot, basically. Now, if we look at a submarine is underwater for a long time. It has a very capable crew. It has great sensors, so that's how it gets its performance. It doesn't communicate it doesn't need to communicate. They prefer not to communicate. They are on their own. They have a full crew with all the capabilities they need, and they have sensor systems. Now, there's a fourth axis on this trade space, and that's price. I have never figured out how I got that fourth axis on there, but the sub, of course, is 10 times more expensive than even the swarm of 100 vehicles like John Delaney's. But it is really the most capable underwater system we have today, and at least in terms of acoustic sensing. So now what do we do with these small robots? Well, we don't have the sensor capability. We don't have the communication capability because we're down here to the 10 to the third, 9 orders of magnitude less. There's no way we can do the centralized control. So what we have to do to get the performance is to add intelligent autonomy in terms of situation. You have to understand what's happening around you, and you have to be able to adapt. You have to make contingencies when things are not working out correctly, et cetera, et cetera. So that's what we are dealing with. Those are the constraints. When we're talking about developing these underwater systems, of course, it all depends on the mission, but the one I've been focusing on is undersea surveillance systems. There's certain requirements. We want to be able to do acoustic remote sensing because you don't want the sensors to run around and touch everything. So we're talking about coverage of orders 10 to 100 kilometers for each node, and resolution of order 100 to 1,000 meters in our surveillance. We have to be aware of the environment because otherwise we cannot adapt to it. We have to be aware of the tactical pictures, where the surface ships so we don't run into them or get run down by them, for instance, using AIS information. Persistence, that's a key. Nowadays we're talking about 30, 90 days of deployments, and maybe at full water depth, 6,000 meter water depth. The most important one is resilience. And it's something that we often as engineers don't think about, because when we are developing algorithms, if you're doing signal processing, for instance, and oops, that doesn't work quite right, we'll tune the tracker a little, stop the process, redo it, etc. You don't have that luxury if your vehicle is at 6,000 meter depth. So robustness to planned and unplanned event is absolutely key to the resilience of these systems. You basically have to be ready for the Apollo 13 event, which of course is unpredictable, but you have to be able to act to it. You have to have some systems in place that can make the decision making for when those things happen. False alarm control is very important. You don't run off just because you hear something. You have to make sure it's the right thing you're running off for. And then, of course, we have the constraints, and they're listed over here with that. But again, as I mentioned, the most important one I find is in my experience, is the communication environment. So then to define what I call nested autonomy is an autonomy system that is able to adapt to the tactical and environmental situation. So the sensing node, the basic idea is that each node has to be capable of completing the mission objectives on its own. If it's cut off from the rest of the world, it's maybe not doing the mission perfectly, but it's capable of completing the mission without talking to any other vehicle, without talking to the operator. It has to be able to do that. On the other hand, when we have connectivity, we'll take advantage of it and do collaboration between nodes. They have to be, as I mentioned, mission resilience. They have to be capable of reacting to a full spectrum of predictable and unpredictable events. And we do that with the behavior-based autonomy that is basically that has the behaviors in there but has no scripting. It has behaviors in there that allows it to react to these unforeseen events. And then persistence, because on the previous slide I had the typical battery life you have nowadays, maybe allows you to run 10 days on an AUV. We wanted 90 days. How do you get there? Well, you can keep developing power technology, but also you can use intelligent ConOps shutdown systems, drift, and if you don't have to do anything, etc., that is really a key to many of these systems. Finally, the way we do this is really to do what I call integrated sensing, modeling, and control, which is where the idea is really that we have to have everything on board that allows us to complete the mission and take the proper action in these contingencies. So the way we do that is automated processing of data, makes sense, of acoustic data, non-acoustic data, etc., and you're doing all the data fusion on board in support of the system. Then you are able to model what is going to happen, because these vehicles, they move at a relatively low speed. The ocean is changing, so it really doesn't matter what happens at this point in time where I am. What matters is where am I, where is my target event that I'm looking at, minutes, hours from now, because that's really what affects my decision making. So we have to be able to model and forecast on board these vehicles, because then remember, they have to do it on their own. And we have this intelligent decision making, which is really the key enabler that's based on the situational awareness, looking at what's happening, and then having these behaviors that have a built-in, that really have represents the strategies that we have built into the system for how to react to these situations. And then finally learning, which is something we're going into, and which I'm going to talk a little about later on. So really, another way of looking at this is that we really want these nodes to be a complete vehicle, just like a submarine. And we talked about the submarine. And so what we want to do is we want to clone everybody that has a role on that submarine. Or in most of what we are doing is research. So it's we have a chief scientist that's deciding what to do. So I have John Delaney up here as an example of a chief scientist. So we basically want to clone John, putting him down there so he can make decisions and tell the captain, as the chief scientist will do on a research vessel like the Alliance, Captain, I would like to do this and I'd like to do that. Now the captain, and here I have the admiral, who actually fills in a role both as a fleet commander, but he also has a background as a submarine commander. So the captain of the ship is really the one that actually executes the chief scientist's instructions, and he does so. Maybe he says, no, I'm not going to do that, because he has a lot of other objectives. First of all, keeping the crew safe, keeping the ship safe, not using too much power, not using too much water, whatever it is we're talking about. So that is where these two really have to be there together and make the proper decisions. And then we have the people who are actually doing the signal processing, for instance, or the acoustic modeling, etc. So I'm just an example. As you note, I didn't include the previous speaker on this because we really don't need the policymaker on board the vehicle. He's doing a much better job and more important job in raising all that money up from his office in Brussels. So I put Toby, who is a past student of mine, who was at the meeting, because I had to have somebody in the picture who was at the meeting, but he happens also to be our communication expert, and he's giving a talk later on Thursday on that. So we have to clone Toby as well. One thing we are excluding is the lower level platform control, and I'm going to, because we have a lot of different manufacturers of underwater vehicles out there, and rather than buying a blank vehicle from them and then trying to do the dynamic control of the vehicle, etc., we don't want to do that. The vehicle manufacturers are much better than that. So the lower level vehicle control, the native software that allows the vehicle to react to commands of what the captain will usually do is saying speed, heading, and depth. We'll let the vehicle manufacturers make the software that actually makes that into actuator commands and also provide the basic navigation, which is feeding back to the captain of the ship. So we're not dealing with that, and I'm going to talk a little more about that later on, how we separate that out. But that's an important component because it allows this crew to really work on any research vessel in the world or any submarine. It really doesn't matter because the roles are the same. And the captain of one submarine can just jump on another one, and it doesn't even have to be the same make. They do that all the time. Okay, so in terms of the design approach we then have adopted for developing these systems is first of all that since we want to clone these guys, these domain experts, there's nobody really better at doing that the domain experts themselves. Now, they may not have all the skills for doing that and putting that into codes. Maybe they aren't able to write C++ code, or maybe they don't even know what a computer looks like. So they need some help. So we need the computer scientists then to develop the cloning tools. So that is the system architecture, and I'm going to say a few words about that. The middleware, how are these various processes, the sonar guy and the captain and the chief scientist, how are they talking to each other? And an example is MOOS, which is made by Paul Newman at Oxford, and which we are using, and I'm going to talk more about that. And then with the decision making, which is then taken care of by the in our case, by the IVP, which was developed by Mike Benjamin. And then we have the domain experts developing the applications, like applications for your cell phone, whether it's in sonar processing, modeling, et cetera, that's what they're focusing on. You don't let the computer scientists do that because they probably don't have a clue about what's happening out in the ocean. They don't have a clue about the acoustic environment, et cetera, et cetera. They know a lot of other things, but they don't know that. So this team is absolutely critical. And then finally, think out of the box. It's not a manned sub. And there are things you can do that you cannot do with a manned sub, and I'm going to give an example in a moment. And you shouldn't be too risk adverse because it may keep you from doing things that you could do. And then the thing that we have found to be extremely useful is to work with an open software architecture, because it allows these domain experts to actually get templates, actual source code, where they just need to put in 2 or 3 lines of a particular algorithm, and they have an operating application. That's an extremely, we found that to be absolutely critical to the development of these systems. Further on the design principles, there are really 3 basic components. The first one is the separation of the payload from the base vehicle. And that's what I talked about earlier. We don't want to bother with the lower level control of the vehicle. We let the manufacturers do that. We'll take care of the payload, but we are taking the captain of the ship. He goes into the payload. The payload software is run using a middleware, in our case MOOS, and then you have these applications. So all you need to know is really the interfaces between these modules and the middleware, and that interface definition is really what guides the application developers, which then are these various domain experts, the acoustician, the signal processor, et cetera, et cetera. There's one process, that's a helm, that's a captain. And the captain has a set of predefined modes that is coded into the vehicle ahead of time, but these are not fixed, they're not scripts, they're just modes he is in. And I'm going to say a few words about that. And in each mode, there's a set of behaviors defined, and these behaviors, again, are not fixed, they're not scripted. A hexagonal loiter can be put anywhere in the world, any depth, et cetera, et cetera. But they are basic behaviors that represents the expertise of these domain experts as well as the captain. Don't run into something. By the way, this concept was developed by David Battle back in 2004, Paul Newman develop MOOS back at when he was at MIT in 2002, and then Mike Benjamin, who was still working with me, developed the IVP, really the key captain of the ship in at Newark, and he's now working with us at MIT. So how does that now look on the actual vehicle? So here you have the cloned guys, the sensor management, modeling, etc., the mission manager, the admiral or the chief scientist, the communication, and the captain of the ship with the modes and the behaviors predefined. It's all connected to this middleware. Now, there's the important thing to take away from this is that there's really only 3 connections from this system, from all the colored boxes, which represents what we call the payload autonomy or the platform autonomy. There's 3 connections to the outside world. One is the sensing system. Another one is the vehicle dynamics. So that is what comes with the vehicle I buy. That's what the manufacturer is taking care of. But that interface is well defined, and that interface can be well defined. The last one is the communication, the interface to the modem. Again, that can be defined. So those are the 3 connections to the outside world. And that's going to be important later on when we talk a little about simulation. So moving on, the concept of operation then is that we define this hierarchical mode structure, and this mode structure happens, we didn't know that when we started up doing this, but it actually happens to be more or less unchanged, going from one mission to another mission, whether it's for oceanographic measurements, for acoustic measurements, etc. It's basically the same kind of thing. There's some deploy modes. You can do deploy in lawnmower, you can deploy in hexagonal loiter patterns, you can do racetracks. In depth, you can do yo-yos, you can do constant depth, etc., etc. And then, reacting to events in the environment, we go prosecute. First of all, we search for the event. Where is it? Then we try to classify it, figure out what is it? Is it actually the front I was looking for? And then finally going in and mapping and tracking it. And all of this has to be built into the modes ahead of time and in the behaviors, except there's one very important feature here, and that is that all these behaviors are dynamic, as I mentioned earlier. So even though the behavior says, well, this is how you do a hexagonal loiter pattern in depth, that's all that's coded in there. The radius, the depth, how many, is it a hexagon or an octagon or whatever, all that is programmable with very simple commands from the top side or from the onboard chief scientist. So how does this work? And this is an example. So here you have these 2 vehicles. These are surface craft, Gilda and Henry, and they have this pretty stupid mission of running in a hexagon and then just going over and switching space, one going over to the other one and vice versa. All these guys communicate to each other as a status, basically navigation information, where am I? So what you'll see is that Gilda has, and this is the way the behaviors work, is that we basically onboard generate in real time an objective function, in this case for speed, which is a radius, and heading, which is the azimuth. Red means it's a desirable one, blue means don't go there. And what you see is that when Gilda is starting over here, it has a red going east, and that's what happened in a moment. That's all it knows. Then at some point it gets a message from Henry, I'm on my way. So then you see this blue region that's pointing towards Henry, I don't want to go there. So this is the way the captain is making the decisions. He basically the domain experts are developing these behaviors with Mike Benjamin's algorithm, put them together in a very efficient way, and then the captain just says, okay, I have a peak at this speed, this heading, and that's what we're going to do. And that's what, in this case, is allowing these to do this while avoiding running into each other. And a lot of this software is available. You can download. There's about 100,000 lines of public code, and there's a lot of documentation, and I'm not going to spend time on the details, but you can go in on the web and find it. You search for MOOS-IVP, and there's a lot of material available. These are some of the vehicles, some of them that have been adopting the MOOS-IVP autonomy infrastructure. The latest one, which is actually happening right now, is Phoenix International. I don't know if Phoenix is known on this side of the Atlantic. Phoenix is the surveying company that was running the search for Malaysian Airlines 370 with an underwater vehicle, and they're switching now to our MOOS-IVP software infrastructure. Basically doing this nested autonomy, platform autonomy we are doing. So the way we have this organized is in a nested repository. Paul Newman is maintaining MOOS at Oxford. At MIT, Mike Benjamin is maintaining the MIT tree, and these are just some of the MOOS represents, I think, what does it say, 8 man-years of development effort. It's very small, totally self-contained. There's no dependencies. Mike Benjamin's in the MIT tree represents about 27 man-years. And then there are other repositories for specific government programs, et cetera, that are nested around these, but these are the basic ones. And it really is a roadmap for collaboration, because what did we do at CMRE in 2008? Was basically adopting this software, putting it on the OEX, and there was one, Marco Mazzi, I don't know if Marco is here, he and I, one night on the Alliance, conspired to put the payload autonomy on the OEX over the objections of his boss, who went to sleep a little earlier. So Marco worked all night with one of my engineers, and we had the MOOS-IVP software running the OEX in the next day. And the rest is history. These are the MOOS apps and behaviors that the center has been developing since 2008. And this is, I'm sure this is incomplete. It increases every day. They just came back from a cruise in Norway where they used all this stuff as well. So at MIT, we have various projects that we have the basic MOOS-IVP development that's funded by Battelle and by ONR. We're involved in a couple of DARPA programs for deep ocean active sonar programs. Then our students were involved in the Robot X competition in Singapore last fall with this surface craft, and they actually went ahead and won the whole thing. So we're pretty proud of that. And there's a paper being published. We're working with Olin College, and Drew Bennett from Olin is here with some of the students he had involved in that program as well. Mike Benjamin is really fond of competitions, so we have this hunter-prey competition where you have one team running an underwater vehicle in the Charles River, another team running a surface craft with a sensor, and one having to track down and drop virtual depth charges on the other one. He's also doing a lot of work on the collision avoidance. You saw the collision avoidance earlier. That was a pretty standard collision avoidance with no rules guiding it. Colrex, of course, the official rules, and we are doing a lot of stuff. In particular, a couple of our Navy students is involved in developing collision avoidance behaviors for surface craft that are consistent with the Colrex regulations. Another competition is Aquaticus, which is just starting now under DARPA funding. It's a competition where you have a manned surface craft, MOOS-IP as it's called in this case, and an autonomous surface craft working together, basically playing a game on the river playing against other teams for gaining some objective. So I'll say a few words about the simulator, and these are some of this is really the motivation, and the motivation is really that, first of all, that that at-sea experiments are extremely expensive, and we have been lucky enough that we could work with the center on doing a lot of our experiments at sea with them. But it's not enough. We have found that we need about 1,000 times as many hours for testing the systems in virtual experiments, or in actual or virtual experiments, as we have time and money for doing with real research vessels. So we need a virtual environment. It's obviously, when we are doing environmentally adaptive sampling, collaboration, etc., it's absolutely crucial that you have high fidelity simulations of the environment. And it has to support, so the simulator has to be able to support both the adaptive and the collaborative aspects. So this is the way we do this. I mentioned earlier that each node has an autonomy system that only has 3 connections to the outside world: the modem, the vehicle dynamics, which we call the front seat driver, and the sensors. So this is what happens in the real ocean. Messages are passed from acoustic modem to an acoustic modem on another vehicle, or up to the top side, and that's basically the environment we are dealing with. Now, how do we simulate that? A little more complicated, but basically the same idea, because we want to make sure that we have exactly the same software running in the payload that we would have in the real experiment, because that's the only way you can guarantee that it's going to work exactly the same way when you get out in the ocean. So then what we need is simulators for the sensors, for the dynamics, and for the modems. So the way we do that is we have a separate computing environment that is running ocean models, in this case the MC's, the MIT ocean circulation model, that's generating realizations of a virtual ocean with currents, temperatures, et cetera, et cetera. And we have acoustic models. So, for instance, when we want to communicate from one vehicle to the other, from this case, if Mako wants to communicate with Hammerhead, the modem, the message is sent to the modem as if it was a regular modem, but without totally transparent to the payload autonomy, that actually goes over into this central environment that's running a communication model that is modeling the range of the communication, the success rate of the messages, etc., and then it predicts whether Hammerhead is going to receive it or not. If Hammerhead is going to receive it, then it sends it to Hammerhead. And the same with the acoustic sensing. We send requests over that then uses the ocean models to update the environment, run the acoustic models for the sensor system. So then I have a few minutes for a few examples. The first one is something that's really actual. We're going back to the Arctic. Haven't been back there it's 20 years ago. We had the last ice camp with the MIT group doing Arctic acoustics. We now have an opportunity for going back. So one of the things we then are looking at is how do you localize an acoustic source? And the one we are specifically after in this case is identifying regions of the ice cover that are active, because that'll tell us something about what is breaking away and becoming a danger for shipping, et cetera, and in general for understanding the change in the environment. The Arctic environment is characterized by this monotonically increasing sound speed profile, which creates this propagation environment that here we have in the contours in dB of transmission loss. The source is up here, and the color indicates the level. And we have some shadow zones here and there. So the idea then is now if we have an AUV down there somewhere at some depth, and we want to localize and track some of these active ice zones, where should we put ourselves in the water column to get the longest range of the tracking of that ice event, and not only is that dependent on transmission loss, it also is dependent on the ambient noise. So the ambient noise is playing into the picture as well. So all this, again, remember, the vehicle has to be able to do this without communicating with anybody. So how do we do that? Well, we do that with this onboard modeling and prediction infrastructure. So we have a sound speed profile. We have some noise historical noise data versus depth. This shows a typical deep sea noise level profile versus depth. And then we use the acoustic models then with that sound speed profile to predict the propagation, and in this case it tells us that to reach that that event in the ice, which happened to be at 45 kilometer distance at this point, I have to be at a depth of about 2,000 meters. And then so what we do then is translate that into an objective function for depth, which the captain of the ship will see then and say, okay, here's my peak. I go to 4,000 meter depth, and that's where I'm gonna be. We do that with this infrastructure on board, again running MOOS as a middleware, and we have a modeling infrastructure using the bellhop acoustic model for doing onboard real-time simulations. And this is just an example from the simulator of what the vehicle was doing for tracking an acoustic source to long ranges. Let me just finish up with this last one. I think I have a couple of minutes yet. Is that correct? And mine says 38. So the traditional way of towing an array is with the array being horizontal. If you talk to submariners, they'll tell you, well, if the array isn't horizontal, it's really useless. So again, I mentioned this idea of thinking out of the box. With the AUV, we have the luxury, we can yo-yo. So why not yo-yo with that tow array? So instead of then measuring we have this cone ambiguity of a towed array, and we would like to know what does the noise picture look like in the horizontal and in the vertical. This doesn't tell us that much because we have this ambiguity between horizontal and vertical. Sorry. If we do it this way, we can break that ambiguity. So this is how that sound picture, the sound vertical, horizontal for an acoustic source in the ice. We have these two peaks, but they're smeared out. In this case, we are doing a horizontal survey with the towed array. If we do the yo-yo, this is what we get. So now we really split them up, and if we compare the two, you'll see the peak we are getting is first of all is much narrower for the yo-yo. But even more importantly, the peak is 3 to 6 dB higher. So by doing a yo-yo instead of doing a horizontal survey, we can get 3 to 6 dB higher signal excess, which is absolutely tremendous. I had some stuff on machine learning. I'm going to bypass that because I'm already over time. But it's basically more of the same message. So let me just go back to the John Delaney's. I have to show this. So, oh, sorry. So this is some work we are currently doing on swarm autonomy. So the question is how, if we have a swarm of underwater vehicles, each of them carrying some sensor, oceanographic sensor, acoustic sensor, whatever, and we want to them fly in a certain formation in a current field that is highly inhomogeneous, highly stratified. How is that happening? And we've developed autonomy, or we currently are developing autonomy for doing that using navigation only to the closest neighbors. We're talking about communicating with within a few hundred meters using high-frequency acoustics, and then navigating the whole swarm with only relative navigation. And this is my version of John Delaney's movie. So here the mode it's set up for is each vehicle is communicating with its closest neighbor every 30 seconds, and they are instructed to make this formation that looks like an arrow. So I think you can see this. You can see this arrow, and now this is a current field that's now moving this formation along, and every 30 seconds they get a measurement of range and bearing to a few of its neighbors, and then they correct. This is done in 50 times magnification of the speed. So as I said, I am notorious for going over time, so let me just go on to, I want to say a few words about, if you'll allow me, Andrea, of talking about education, because we have this new class that really is focusing on these concepts on the interplay between communication, sensing, and autonomy. We just finished last week with the students having a competition where we generate in the simulator, we generate a front, and you can see it's a moving front, it's a sinusoidal shape. The students don't know what the actual period, wavelength, etc. is. It can look like this, it can look like that, but they have to estimate these 9 parameters characterizing the front. And a couple of the students came up with this one, and this is really the essence of doing adaptive ocean sampling. First, the vehicle is running around in a circle, estimating the slope of the front. That's this line. Then once that's estimated, it goes in and does an adaptive survey along the front, back and forth, and it's doing that with basically building three autonomous behaviors. And they do that first in simulation, and then they do it on the river with the surface craft, and then that's there they go. So then of course what they discover is that when they're running in the simulator, they can run a time warp of 30 or 50, and if something doesn't work, oops, then we do Control-C and restart, and once they're out there and they're running with no time warp, it's too late. Then the autonomy system really has to be able to do the whole thing on its own. So that leads me finally to the summary, I think the main takeaway is that the autonomy really is a key to developing a persistent ocean observation system because of this really constrained communication environment that we are facing. That is the main driving force. Thank you, and sorry for bringing it up.